In this video, I'll provide a brief overview of how our paper on layer-wise compressibility can extend a number of methods within NAS. Zero-cost proxies have emerged as a low-latency approach within NAS, where a zero-cost proxy receives a neural network as its input and performs some calculations which hopefully allow you to distinguish the good from the bad network designs. In this paper, we attempt to explain and extend a number of existing proxies. Many zero-cost metrics are developed out of the pruning literature, in which the importance of every parameter in a network is measured via saliency scores. Three of the most common are on the screen, these being SNP, GRASP, and SYNFLO. To turn these parameter level scores into a single score for the network, they must be summed up over all the parameters in the network. This approach of naive saliency aggregation potentially discards important statistical information. And among existing metrics, ZICO stands out as both an empirically strong method and one that goes beyond mere saliency aggregation. To summarize the formulas on the screen, ZICO takes a signal-to-noise ratio, the gradient of the input data. And in this sense, ZICO is a measure of saliency compressibility over the data samples. The intuition being that a high variance gradient is suggestive of training dynamics that are dominated by a small subset of the data, preventing the network from effectively using all available inputs. Motivated by this, we consider whether assessing compressibility over the parameters may also prove insightful. Therefore, we propose a measure of parameter compressibility, SSNR, which takes the signal-to-noise ratio over the parameters. Intuitively, a high variance saliency over the parameters means that only a small subset of the parameters are highly important and the rest are somewhat redundant, potentially preventing the network from learning effectively. In both ZICO and SSNR, we measure the compressibility over each layer, and we do this in order to remain consistent with a number of conservation laws for neural networks. However, we wondered whether this idea of layer-wise compressibility could be extended beyond just saliency scores and also applied to activation patterns. And we believe that an existing metric, NASWAT, already does this, whose formulas on the screen, where here CI corresponds to the activation pattern for the ith input data. However, we observed too that NASWAT could be improved through a layer-wise partition. Therefore, we generate a gram matrix for each layer's activation pattern and sum their log determinants to produce a layer-wise version of NASWAT, a layer-wise measure of activation compressibility. Upon noting a number of dissimilarities between our layer-wise version of NASWAT and SSNR, we determined that they may be ripe for combination. And as such, we take their layer-wise dot product to produce a topological proxy for compressible expressivity, trainability, TSET. TSET improves upon SSNR in a number of search spaces and provides a proof of concept for direct metric composition, an as yet unexplored area of research. We found that SSNR and TSET consistently outperformed state-of-the-art metrics in almost every search space in which we compared them. For brevity here, we can see just the results of NASbench 201 and a more practical search space of ZenNAS. We can see that taking the signal-to-noise ratio of the SNP scores, SSNR, drastically outperforms mere aggregation, which is just listed as SNP in NASbench 201, but more generally we can see that both SSNR and TSET outperform many previous existing proxies. These results hopefully demonstrate the benefits of viewing zero-cost metrics through the lens of layer-wise compressibility. And if you're interested in more details about this, then please check out our paper.